Okay, so today I would like to introduce the Malthus law. The Malthus law is a law that is introduced in differential equations usually, and it's one of the first laws that once introduced because it's really easy and trivial. So it's a good way of introducing how to make a model for certain situations in life. So Malthus was an economist. His name was Robert Malthus. Excuse my English. And he was an English economist. And what he said, this was, by the way, in the 18th century. So what he said basically is that the population was growing so fast that we would reach a point in which food would be too little and we will go into a progressive poverty. So basically that's the claim he made, like population growing very fast. We'll know now what growing very fast means. And basically what he says is that food or resources growing slower. And we'll also introduce what growing slower means actually. So basically one reaches a point in which we have a catastrophe. And this is the Malthus catastrophe. So basically it's a catastrophe because of course if the population grows faster than the food, people are gonna starve, okay? The thing is that it was proof that actually this is not real. It could happen at the beginning of the 18th century when resources were very limited, but within the years, it seems that the mortality and index of natality were quite stable, so mortality decreased. Greatly, and also not so many people were being born. So this led to sort of stabilization, which actually the catastrophe wouldn't happen, okay? This led to something called the demographic transition, which is a whole new theory on how population and resources are more or less balanced. But anyways, we are interested in studying this Malthus law, even if it's a bit out of the question right now, because we have stabilization, but it still is a really nice model to see how the population could grow faster and we could reach this point a few centuries ago. So let's introduce this through differential equations. So the point of this video is to see how a very simple problem like this can be modelized by some differential equations that can be really easy. One of the first main kinds of differential equations and how they can be solved very straightforwardly. Of course, when one needs to have a little bit more intricate models, this is not going to happen. And usually differential equations will have to be like either really intricate differential equations. Or what's going to happen also is that we won't be able to solve them analytically. So that's when numerical methods take place. We'll actually take a look at this a whole series of videos to look at some numerical methods. But for the moment, let's start with the simplest differential equation. This is an introduction. This is my first lesson. So let's see how we can write down this problem in terms of this equation. So now I'm going to introduce some variables. So I'm going to introduce the variable P, which is going to be the population. And obviously the population is going to be a variable that depends on time because the population is going to be changing. And also we're going to have another variable that we're going to call A, like for amount of food. That is available. So of course in time the population will be growing. And the amount of food, although it can be growing, it's going to be less all the time. So it's going to be growing, but it's going to have a different type of growth. So let's propose the model. So what he said is that population is growing as a geometric series. And the amount of food is growing as some series or progression. Maybe let's call it progression, like a geometric progression. And the sum as a sum progression. What does this mean? Well, basically, this means that for the amount of food, we're going to have a growth that such that the amount of food, how it changes with time, this is what the differential means, is going to be constant. Let me call it constant K times A0. It could be called any constant, whatever you want to call it, like K tilde, okay? I'm just going to call it this way, KA0 for convenience. Okay, so this is convenience notation. So that is what basically means that the way that the amount of food is growing is linear. And what the model is supposes is that the population now is growing as a geometric progression. So that means that how the population changes in time, which is what is represented by this, it's proportional to the population at any time given. So here we have some parameters. We have R, which is the constant of proportionality. Proportionality, excuse my English, of the population. And here we have KA0, which is the constant of proportion of growth of the amount of food that we have. Okay, so basically right now we have two differential equations that they are very simple. One, which is the one for the amount of food that we're gonna integrate right away. realize that for integrating a differential equation, what one needs is to put all the dependent and independent variables to both sides of the equation, to separate them. And we are very lucky because this is a very, very simple differential equation, which is all a constant. So we can separate the variables at, which is a dependent variable, and t, which is time, which is the independent variable. We can separate them really easily, as simple as leaving the differential of a on the left-hand side and leaving the differential of t on the right-hand side. So that means that we are separating both, because here this is all a function of a and this is all a function of t, since we have a constant. So starting from there, this is a very simple equation that we can just integrate very straightforwardly. So we are going to integrate it from an amount a0, which is going to be the amount of food in the initial time, say t0, to some amount at, and the time will go from the initial time t0 to t. We can consider t0, which is the initial instant. For convenience, we can just say that it's 0. Okay, so we start like in the start time. So this basically means that if we integrate the left-hand side, we only have that at minus a0 is going to be equal to the constant of integration and the integral in between t0 and t of the differential t. This is straightforward again, and we get that a is a0 plus k a0 t. But we have considered that t0 is 0. So this is linear growth, as you can see. We can actually rewrite it if we want as a0 common factor. A0 is a common factor of what? Of 1 plus kt. Okay, so this is linear growth of the amount of food. And now, well, we're going to see how's the growth of the population. So we have this equation. Sorry, this is a bit tricky. It's my first time making a video, so excuse me for my English and excuse me for the bad handwriting that I'm realizing that I have. But mathematicians can be a little bit messy sometimes. So this is the second differential equation that we have to integrate. It's also a very simple equation. It has separate variables. As you can see, we can put everything on the left-hand side. That is only depending on p. And well, it's obviously depending on t too, but it's implicit. So that's the key. And here on the right-hand side, we can leave all the dependence on t because r is a constant. Bear that in mind. So now we can proceed to integrate very straightforwardly. We can integrate on both sides of the equation from a population p0 to a population pt, and from instant t0 to t. So here on the left-hand side, we have the Neperian logarithm of pt in between p0 and pt. And here is a constant, it's going to be multiplied by t, because I'm taking t0 to be 0 again. So we bear that in mind. So what do we have? Well, we have logarithm of pt minus logarithm of p0 equals RT. And we can rewrite the logarithm of pt divided by p0 equal RT. And from here, we can take exponentials and leave that pt is basically p0 exponential RT. So if R is greater than 0, this means growth. And this is what we are supposing in our model, that the population is growing. Where are we gonna have? We're gonna have a type of growth that is gonna be exponential. Okay, so PT has exponential growth, whilst AT, the amount of food, has linear growth. Basically, it means that PT is gonna grow very, very fast, while AT is gonna grow linearly. So basically, more people than food. So how can we measure how much food we have per person? Well, we can just basically define a new variable we're gonna call AT, which is gonna be just how much food per person there is in the population. So if we define this to be A divided by the whole population, and considering that A was let's see where it was, it's A0 plus KT, and here PT is B0 exponential, we can define an A0 times 1 KT, where A0 is just A0 divided by P0. Basically, this is the initial amount of food per person. Okay, so now we have how much amount of food we have per person in every instant t. We can write it like this. And as you can see, it's an exponential that is negative, okay, because R is positive. So that means that a long time, AT is gonna tend to 0. So basically the food per person is gonna be tending to 0 when there passes like some a specific time. So when will we be that time? Well, if we define a minimum to be the time, well, it's gonna be the minimum food per person in order for the person to survive, and we call TC like critical time. For a person, what critical time in which a person has the minimum food, in which a person has minimal amount of food what can we reach to? Well, the time in which the amount of food in the critical time will be A0 according to the integration of our differential equation, K, which is a constant of integration in T critical times the exponential of minus R T critical. Okay, and we say that in this moment, the amount of food in this time critical is gonna be less or equal to a minimum, which is the minimum amount of food per person. So here, if we put it this way, we can write it as, sorry, this is possible. If we put it down as less or equal to a minimum divided by a0. So this condition is what is known as the Malthus catastrophe condition. Malthus catastrophe condition. And as you can see, this has been a very, very easy model, which is true that it's not that we're using it now because it's from the 18th century. But at some point, this could actually modelize how there could be hunger a few years, centuries ago, just by thinking that the population is growing faster than food, and how they grow, like this one exponentially, as we can see, and this one linearly. And as you can see, both differential equations have been super easy. They are very basic differential equations. Well, let's put it before separation of variables, in which we have separable variables, in which we can actually find the primitive, straightforwardly. Which is not usually the case. So as we proceed with these series of videos, we will solve lots of differential equations that actually are not gonna be as easy as this one. But we'll be progressing little by little and introducing all the different knowledge that we need in order to start integrating some more complicated things. And also we will do some numerical. So for the moment, I hope you enjoyed the Malthus catastrophe. And although it's very easy, it's really intuitive for any person to understand it. So thank you for watching.